Okay guys, last time we introduced you guys to igneous rocks. We also introduced you to the different types of magma that we have out there, the felsic and the mafic magmas. Now if you remember, which one of the magmas has the lower viscosity? Okay, which one has the lower viscosity? And there's a hint here, the higher the silica content, the more viscous it is. So something that has low silica content has a higher viscosity. Okay, so the mafic materials, if you remember, the things that have more iron and more magnesium, less silica, is going to have the higher viscosities, which means it flows better. Okay, that's important when we talk about eruptions, because if gases and things can come out of the magma, the pressure doesn't build, and therefore you have less effusive, more effusive magmas or eruptions, which means they're not very explosive. Where if you have felsic eruptions, the gases can actually build up inside the magma and the rock to the point where they'll actually explode, and those are very dangerous. Okay, so materials that have high silica content and low temperatures tend to be more viscous, and therefore they're more dangerous in a volcanic setting. We'll come back to that and talk about that a little bit later. Now, temperature makes sense, hopefully. Like we talked about this last time. If we had a bunch of honey and it was nice and hard, and it's kind of been dried out for a little while because some of the moisture is gone from it. It's part of the reason why it's dried out and why it doesn't flow very well, right? But if you add heat to it, increase the heat, the atoms start to move, because that's what all heat is, by the way, is the movement of atoms. And if you increase the movement of that atom, it can actually flow better within the system. It's not stuck into place, it's not as rigid. And so as it heats up, it can flow. And so it has a lower viscosity. It can actually has less resistance to flow, right? The more heat you have, that. Now there's also, this next one here is the silica content. The more silica content I have, the higher the viscosity becomes. It's kind of like if I had water and I continued putting mud in it, right? Or dirt in it. The water is going to starting to become brown, or it's going to become thicker, right? And then if you put even more in it, it's going to start becoming like a mud, or even putting more dirt in it, it's going to become even thicker than that. So this is this same kind of concept. There's some things that make things stickier or stick together, and by adding silica, you're going to add basically your melt is going to be stickier. Okay, and that's also an important concept when you have explosions, or in volcanoes. If you have something that has a high viscosity, it's going to blow up and explode because the gases can't escape. Whereas if it has a low viscosity, the gases can escape, and then you don't have as big of an eruption. We'll come back to that, but just wanted to kind of remember that viscosity is an important concept when we talk about volcanoes. Okay, so how does this magma form? We've already kind of discussed this a little bit, but the increase in temperature happens all over the world, and there's no realistic mechanism for the general cause of this. There are some what we call hot spots and other things like that in plate tectonic our discussion. And we'll talk about plate tectonics more later, and then how this interacts with that. But anytime you have added heat, okay, you can start melting materials. And there's reasons why some things can melt. Okay, so for example, if I have something like this, a material here, and you slowly melt the other rock in it, it can start actually coming into the melt itself and therefore become a magma, right? So it's fairly straightforward. The temperature one is not that big of a stretch for people to understand. The higher temperature you have, the more potential for a magma that you can have. Okay. The next one, which is is one that people have a hard time with, and this is the pressure. And this is if you change pressure, you can actually have induced melting. Okay, so an example of this one here, let's say I had a solid here, and this is what we call a geotherm. Okay, so this is the temperature of material might actually start becoming more plastic, so you can bend it and not as rigid, right? And then when you get past the red line here, it might become what we call liquid, a pure liquid. But you might get some liquid to start once you get past what we call the solid S here, where we're no longer solid and now into what we call this ductile zone, okay, or plastic. And so the material itself, let's say it starts off here, it might have a very high pressure, right, and high temperature as well. We have maybe even 2,000 degrees here, maybe a little less, maybe 1,500 degrees, or 1,900 degrees. That's better. So we have 1,900 degrees, but let's say the temperature doesn't change at all. The temperature stays the same, but the pressure changes. And the way the pressure can change is maybe the whole magma body starts to rise. And if it rises, there's not as much pressure on it because there's not as much material moving on it. And so therefore, it can start to actually melt because of that changing in pressure. Okay, so that's kind of an interesting concept. When you change the pressure, it will actually change the consistency of material. It's kind of like the same thing inside of a pop can or a pop bottle, right? That inside of that pressurized pop can, the material is actually a liquid. But as soon as you release the pressure, all of a sudden that material can no longer stay in that pressurized liquid. It now has to go into a gas, and that's why you get the bubbles and everything coming out of a carbonated drink. Right? It's the same concept. Pressure has this impact on changing the state of some objects, and almost any object in reality. But lots of times it's not within our realm of understanding because it's at too hot of temperatures that we physically can actually be exposed to. So that's one of them, is the change in pressure, and this can happen in a lot of plate tectonic boundaries where you have plate tectonic boundary where the materials are moving apart. And the reason the materials are moving apart is because magma is moving up. If magma is moving up, that means pressure is decreasing, and therefore you can have melting. So you can actually, small volcanic features are places where the plates are moving apart. Okay. Another place that we have it is what we call hot spots, where it's just hotter in that part of the crust more than any other places. So it will actually rise, and as it rises, the pressure decreases, and if the pressure decreases, it gets to be more of a melt. Right, so it can actually melt out that way. Now the last one here is what we call adding volatiles. This also is related to plate tectonics. Okay, and in this case, it's usually by the adding of water. Water is the most common volatile that we have out there. And the most common place that this happens is when you have a plate where you're having two plates coming together, and one plate goes underneath another, usually bringing water down with it, like in an oceanic plate that you see here. That water will be brought down. As that water is brought down, it's released from the as it goes down, and that increased water will now lower the melting point of this material, causing it to melt. Okay, so those are the three ways in which you can get a melt. You can increase the temperature, you can decrease the pressure, or you can add volatiles or add water. Okay. And we'll come back and talk about this in plate tectonics later, but this is something to remember. We'll discuss this again in our next unit when we talk about plate tectonics. Okay, so what happens when you actually have a magma melt? Now I'm going to pause for a second because I need to get something for our display purpose. Okay, so I'm back here. I wanted to grab this bottle here. This is what we call a density bottle. Let me just put it back here. And you'll notice here there's actually... some people might think that this is just really one fluid and these two beads in here, right? Okay, so you have the lower bead and the upper bead, and then this fluid. And then, but in reality, we have actually 5 different materials inside of this bottle. Okay, we have a fluid down here that's actually more dense than this blue beads and the white beads, and more dense than this upper fluid and the last material, which is the air above it, because that actually plays a part in this little experiment here. So you have these different density materials, and this material down below here is actually salt water. Sorry, alcohol, and then the stuff up here is actually salt water. And so the density differences are in here. Now notice there's 2 beads here, and they're floating in the middle. One is more dense than the material above, and less dense than the material below. Okay. So now in a magma, like you see here, in any kind of magma, all those minerals are all over and combined throughout the material, right? So they're all, the mafic minerals and the felsic minerals all throughout the material. And they'll stay with the material as long as the temperature or the pressure and stuff like that is actually keeps it in a melt. But as you actually have magma cool, each of them have a different melting point, right? And as you have that different melting point, you'll notice that the denser materials go to the bottom and the less dense materials go to the top. And the reason is because as these minerals, the darker minerals, or what we call the mafic minerals, actually crystallize, they'll go to the bottom of the actual magma chamber. Whereas the felsic minerals, who are less dense, will go to the top of the magma chamber. Now that's the analogy I do use for this bottle. Now, just to give you a clue of what's happening here is when we have alcohol and salt water mixed together, it actually goes into a separate temporary fluid that's now more dense than the white materials, but less dense than the blue ones, so they separate out. And then as the alcohol and the salt water actually go back to what they were before, you'll notice that the two beads go back together. Well, that's a pretty cool little experiment for talking about density and understanding mixes of chemistry here. But it's also a great way for us to understand the sequences of how magmas cool off. So if you have the original melt is mafic, we have lots of felsic minerals in it as well, right? That's my initial melt with all the material inside of it. But as soon as it starts to cool off, notice the mafic materials will fall to the bottom because they're denser. The felsic materials will float to the top because they're felsic. And so what we end up with is this if this magma continues to rise, we're going to end up with the magma that's more felsic rich. As it continues to cool off, the more mafic material is going to fall out, and it's going to become more felsic and more felsic. So if you have a magma that's slowly cooling off, the magma is going to become more and more felsic over time. And that's what this graph actually suggests, is that the more mafic minerals, as the temperature goes down, are going to fall out first, and they'll fall to the bottom of the magma chamber. So what's continually rising in the subsurface is going to be a more felsic material, leaving the mafic materials behind and having the more felsic material to rise to the surface. And so as you continue to cool off, you'll continue to have more and more mafic stuff falling out until at the very end you have these very silica-rich, quartz-rich minerals that tend to be what we call a felsic magma. Okay. Now these also have to deal with color as well, so we'll go back to that a little bit later. But if you remember, quartz and muscovite and feldspar tend to have lighter colors to them. So you have that's why you have the lighter color within here, whereas mafic materials tend to have darker colors in it. So for example, this rock right here is a mafic rock. It's a mafic igneous rock, and you can tell that it has this nice dark color to it. Whereas this rock right here is Felsic Rock, and notice it has a lot of the whitish colors. There's still some mafic stuff in it that still was in the solution, but the vast majority of it is now felsic, and we call this granite, whereas the last one I showed you was basalt, right? And then there's stuff we can find that's in the middle of these two that's what we would call intermediate. That's more mafic stuff, but not as much felsic. Or we can have almost pure felsic, like this one right here. This is almost pure felsic, and it's actually a volcanic ash from Yellowstone National Park. But the point comes is it's the one of the more, and that's a very, very felsic volcano, and so it's almost pure silica, right? Now that's important because we'll talk about how that most of our plates, our continental crust that we're standing on our continents, are what we call felsic materials, whereas most of our oceanic plates are mafic materials. And we'll talk about that a little bit later. It's going to come back to haunt us a little bit in plate tectonics when we discuss that. So all this stuff is going to come back to and we're going to use it in multiple units after this. So it's important to start now. And this is sometimes people don't like all the chemistry of this section, but it's important, and the physics of this section, but it's important to understand so that we can understand the processes in the future. Okay. So one way that the melt occurs, or the materials separate out, is because of the temperature. Remember, the temperature has different melting points. So as it goes down, different minerals are going to fall out, and you're going to become more and more felsic if the magma continues to rise. Okay? So what's left behind is the mafic material. Well, what if you had a rock, like this rock right here that I have in front of me, okay, that tends to, this one's more on the intermediate scale. It's a little darker than this one I showed you, right? Okay. And so not as much of the mafic stuff has got out of this one, but you can see that if I were to melt this one, let's say it was already solid, and I start melting it. Well, if you remember, the felsic stuff has the lower melting point, so the felsic stuff is going to come out of solution first. So that melt, once again, is going to become more felsic. Even though, and then the mafic stuff, if you don't have enough heat, will still be in its crystal form. But if I got it up to the same temperature, the melting point of this mafic stuff, then the whole thing will melt. But if I only got it up to, like, say, like 800 degrees, where the dark material will still be in its mineral form, but the light material has a melting point around 700 degrees. And so that would already be in the solution, right? So that means your